Please welcome to the stage, Chen and Ravi Sahita.
Hi everyone. Thanks for coming to BlueHat. I almost said Black Hat. I've been in Black Hat too. So we're going to talk to you about sort of a Western take on a story on ransomware detection using machine learning. My name is Ravi Sahita. I work in Intel Labs in security and privacy research.
Hi, my name is Chen. I am a deep learning research scientist in the security privacy lab at Intel Labs.
Okay. So following the legal talk, we have to have the legal disclaimers, right? This is just a quick outline of what topics we're going to cover today on the ransomware detection. We'll walk you through some of our experiences doing this case study in the labs. And our lab works on sort of exploit prevention capabilities as well as machine learning used for exploit prevention. So, following the sort of the Western theme, we'll walk you through what are the good parts about using machine learning for this particular use case, amongst others. What are the bad parts, right, that any researcher or practitioner needs to be aware of when using machine learning for this use case or other? And then what are the really ugly parts that we need to also think about? And Lee will go through those in lots of gory detail, so get ready with your, sort of put your math hat on as well. And then I'll also cover some of the ideas that we can apply here from a platform perspective to build an overall system where we can improve the robustness of this kind of an approach. Right? So we'll start with that. So let's touch a little bit on ransomware, and I think people here are familiar with it, and I think this speaks to Alex's point also in the keynote today morning, is that this is one area where the tools that we have built for better cryptography, new instructions for cryptography, SDKs for cryptography, making it easier for developers, that sort of gets used against us, right? So obviously cryptography is a great tool. It's awesome for privacy and access control, but it also gets misused when somebody uses it as ransomware, right? And it's not hypothetical anymore. It's sort of been in the news for a long time. I mean, imagine like a worst case scenario, like you go into a hospital with a medical condition and you can't get the diagnosis or the treatment because the systems are down because of a ransomware attack, right? And this is not hypothetical anymore. If you just do a Google search today morning, you're going to see an incident that happened that was reported by PBS for a medical institute, and it's also schools, government organizations, everywhere, right? So in this talk, we're going to focus more on the crypto ransomware, which uses encryption to essentially prevent access to your resources and essentially extort from there. And again, this is sort of a flow I'm sure most people here are familiar with, right? There's different aspects to ransomware, like in terms of its life cycle, starting from distribution, getting actually on the platform to execute, communicating to its servers, potentially to use the best form of crypto they can, with the strongest form of keys, enumerating the files they want to encrypt, encrypting the file actually, right, which is the area that we'll focus on in this case study, and then leading to extortion, right? This case study from a machine learning perspective will focus on the encryption aspects and use that from a detection perspective. Let's look a little bit of when we set our mind to do this case study, like what kind of data sets that we focused on, right? And this was just sort of a point in time, right? So the ransomware has evolved from that point on, and there's new forms of ransomware. But when we started this study, we sort of looked at what ransomware families were sort of the most prevalent at that time, and we used that data set from sort of standard sources like VirusTotal. There was a limited amount of time the ransomware can get executed, and I'll talk about some of the limitations and the issues that causes later on. And we use standard approaches here. We use decoy files to check that the ransomware was actually executing, right? And we saw a low activation rate, right? And I'm sure many practitioners here have seen similar issues. But this is just to give you sort of a baseline of what data set we started with. The data acquisition we did was via a Sandbox system that we built in our lab. It's basically a sort of a dedicated system, and this is like a small sort of fragment snapshot of it, right? Where as much as possible we try to avoid evasive malware, things like that, by using bare metal systems, and that obviously is a lot of pain to sort of configure those right and make those repeatable, etc. And then we use some new capabilities in the labs, like doing interesting things on like drive firmwares to essentially do like very fast checkpointing, so that we could like make the system as repeatable and robust as possible, right? And that's how we acquired most of our data set. The data set that we collected was essentially, we said let's sort of keep it simple to begin with, right? So we use a lot of the file I/O telemetry that is available from systems today. And as I said, we focus on the encryption stage of the life cycle of the ransomware. So we collected sort of standard events, like what type of file I/O events are happening, what file regions is it targeting, right? Is it going to the system directories? Is it going to the user space directories? Basically where the data is that the user cares about, and also the entropy of the files as they are changing, right? And those pieces of information are essentially combined that and then used in our deep learning system, right? So with that, let's start diving into the good parts of machine learning, and Lee will walk us through this journey of like, hey, how do we start off building a machine learning model, and then we'll look at the platform aspects after we complete that part. So with that.
Thanks. So let's examine first the aspect of the good part for machine learning at recognizing attacks. So Ravi talked about what the event logs are like. And before we fit into the model, let's first do some feature engineering, feature extraction. And we try to bin the events, and then in terms of the file I/O activities and also the entropy change, and then map that into categorical integer values. And of course, some of the logs are of different length, so we also use zero padding to make sure they're all of the same size, so we can train machine learning models on top of the data sets. So this is what our features look like. So each log is a representation of those integer values from 0 to 9 in sequence. And then we do our training on the data set, where we have the train and test split at 80-20% split. And we use 7 different machine learning models and evaluate a lot of performance metrics on the test set. And our dimensionality, originally we set it to n equals the 3,000, and we can use additional dimension reduction methodologies to train on the models. So we train those 7 different classifiers, including text CNN, XGB, linear discriminant analysis, random forest, naive Bayes, support vector machines with 2 different kernels. And what we have observed is that text CNN actually has the best performance on this data set. And when we look at the results, one thing we thought about is, okay, why don't we also use text CNN as a feature extractor, and then retrain the rest of the classifiers in that feature space? And can we observe a performance boost? And what do we mean by that? So let's have a very quick overview about what text CNN is. So essentially, this is a one-dimensional filter-sized convolutional neural network. It has been shown to perform very well for sentence classification. And here is a architecture picture for what this neural network look like. And what do we mean by the feature space? And here, we're considering the layer before the fully connected layer as the feature space, where we're extracting the representation in this layer. And we want to, because of the prior better, superior performance of text CNN, we want to retrain the other classifiers. So before we do that, we also did a visualization on the distribution between benign and ransomware in the text CNN subspace. And from looking at the distribution plotted in red, as in the malicious samples, and blue, the benign samples, we're seeing the features are well separated in this feature space. And hence, here is the results. where we have the compositions of 2 different classifiers, where the subsequent one is trained on the feature space of text CNN. And we're seeing all of the classifiers have a performance boost in accuracy, false positive rate, true positive rate, F-score, and area under the curve. So this is really great, and this is the good role of machine learning being effective and accurate at detecting attacks. And we also evaluated accuracy, false positive rate, precision recall, F1 scores, but are these things enough when the machine learning algorithms are used in security critical applications? So with that question, we go to the next part, the bad part. Essentially, how we wanted to look at is trying to juxtapose the good cop versus the bad cop role of machine learning and how they can perform and behave. And in this analysis, what we're trying to do is we're trying to identify the vulnerabilities and blind spot of those highly effective machine learning algorithms. And furthermore, we're actually using other machine learning algorithms in order to automatically hack these effective ML systems. So before going into our proposed overview of techniques, let's first talk about adversarial machine learning in the vision space. So adversarial machine learning is a relatively newer emerging field in machine learning that examines the robustness and vulnerability resiliency of machine learning algorithms. And what I have shown here is the adversarial machine learning used in computer vision, where you can have a very highly effective DNA algorithm that have very high accuracy at computer vision classification results. However, you can just add very few perturbations that's imperceptible to the human eyes, but the DNA algorithm will misclassify them. So as you can see, the cost can be high because a stop sign that's originally classified as a stop sign with some perturbation could be misclassified as a max speed 100. In addition to image classification, these type of attacks can also happen in object detection. As we add some perturbations, the sheep are being recognized as cars. So how are we mapping this into the malware space? And our core idea is we're also thinking of some new algorithm called the generative adversarial network. So we wanted to employ the idea in GAN-generated adversarial network into synthesizing some of the adversarial perturbations to spoof the ransomware detection system. So what is a generative adversarial network? So it consists of 2 parts, or you can consider 2 neural networks. One is the generator, and one is the discriminator. So the generator will generate fake samples to fool the discriminator. On the other hand, the discriminator will differentiate or classifies the reals from the fake. So over time, the generator gets much better at creating fakes that look alike the reals. But over time, the discriminator will also get better at classifying reals from the fake. So essentially, this is what the idea of GAN comes from. It's essentially 2 neural networks are playing a 2-player game, and you can consider the generator being a counterfeiter that's trying to make some counterfeits, and the discriminator is the police, and both are getting better by playing this arms race. And it has been adopted and used primarily first proposed in images. As we can see here, initially the MNIST digits generated by GAN were looking like noise. However, after some iterations, it becomes better and more crisp, like the original MNIST dataset. So this is the core idea of how we wanted to build this machine learning-based system to spoof ML. So what we wanted to propose is we also have this generator and discriminator, but we will have the generator to generate the dynamic execution of the sequences that we showed earlier in our data set. And then we'll have the discriminator in order to try to differentiate the real and the fake. And over time, we would hope to get a very good generator that can synthesize these type of adversarial ransomware sequences that can spoof machine learning algorithms. And furthermore, note that we are proposing this technique not in the vision space, but in a malware space. So typically in GAN, when you're proposing generating images in the vision space, the human eyes can be one of the metrics to stop training, as long as it looks somewhat like the digits or it looks somewhat like a real human being, you can stop the training. However, in our case, the human eyes is not applicable here. What we wanted to do is we want to make sure the adversarial examples we have generated from GAN actually possess some maliciousness. So we actually proposed two sets of adversarial quality assessment metric. One is sample-based, one is batch-based, so that we evaluate that the adversarial samples truly possess maliciousness. So given that, here is our overview methodology. So we have those samples that's collected from our sequence ransomware logs. And then we train particularly a AC GAN that's also not only on fake and real, but also conditioned on benign and malicious labels. And once we have trained the neural network, at test time, we would generate the adversarial malicious samples. And we incorporate this quality assessment check on the generated adversarial examples. If it passes the assessment check, we'll put them in our set for later to bypass the ML systems. If it doesn't pass that, we will go back to regenerate more of the adversarial samples. And finally, with all the generated adversarial samples, we will send them into the highly effective machine learning classifiers that I have shown earlier, and then understand how well they can detect those adversarial examples. And here is some more details in how we train. Typically, when training GAN, there are some mode collapsing issues, and also when we stop, because the loss function is a combination of the generator and the discriminator. And so we have some more technical details in this aspect. But at test time, we will generate 5,000 malicious samples and test whether those highly effective ML algorithms can detect them. And all of those samples actually did pass our assessment, adversarial quality assessment. So here's the result. As we can see that out of all of the samples we have fed into the ML system, only one classifier, support vector machine with a non-linear kernel in the textiness space, does not get fooled by the adversarial examples, versus all these other highly effective classifiers actually fail to detect the majority of those adversarial samples. And this clearly indicates a very broad attack surface for machine learning systems. Hence, here comes the bad summary. So what we have proposed here is that machine learning algorithms can automatically hack other machine learning systems. As we have demonstrated here, the generative adversarial network can serve as an intelligent hacker to bypass those highly effective ML systems. So from this case study, it definitely demonstrates that robustness and resiliency are equally important as accuracy, false positive precision, recall, F1 scores, especially when we're building ML classifiers for security critical applications. Now, one of our goals is to try to understand why this happened. So we dive deep to investigate what happens in a boundary decision such that in the original feature space, these samples are very malicious, very close to the malicious real samples, and they do possess maliciousness. However, the classifiers who are highly effective just really fail to detect them. Then here is our ugly part, which consists of the investigation and also some other aspects that we should address and consider when we build machine learning algorithms. So we investigate why the generated samples can bypass those machine learning systems. So we have a 2D visualization here, where the red corresponds to the ransomware cluster, and the blue is the benignware cluster. And we also plotted the adversarial examples in this 2D plot. So the adversarial examples are in the dark red small cluster, as we can see. And they lie pretty closely to the boundary, but much closer to the real benign, particularly in this text CNN feature space. So recall that all these samples actually passed our adversarial assessment quality check, but when they are mapped in this highly effective feature space, they actually get mapped from the red part to the blue part. On the other hand, we consider what about other type of boundaries. So if you remember, in one of the 7 classifiers, support vector machine with the nonlinear boundary actually was able to detect 100% of the adversarial samples. So we plotted the nonlinear boundary and then understand where the adversarial examples lie. And in this case, what we're seeing is that the nonlinear boundary actually do demonstrate some level of robustness against adversarial examples, and this indicates they seem to have a smaller blind spot. But there are other issues that we should consider. So for instance, concept drift. When your samples are varying and changing over time, how can you make your machine learning system more robust against the samples that are morphing over time? And another aspect is time variance. For instance, if your ransomware takes much longer to encrypt the data, will your machine learning algorithm be able to capture that prolonged behavior? Hence, there comes our ugly summary. So we have investigated the machine learning boundaries and understand why the adversarial examples are easily being classified as benign. And we show that in the original feature space, the adversarial examples are indeed malicious. However, in the feature space, when it maps to the feature space, it's actually closer to the boundary decision. That's why they get misclassified. And we also examined the linearity and the non-linearity of the boundaries. And it seems like the nonlinear boundary decision will show better resiliency against adversarial examples. Okay, so next I'm gonna pass the presentation to Ravi to talk about how our platform capabilities can improve detection to make the attacker's job harder.
Thanks, Lee. All right, so hopefully with Lee walking through like the 3 phases that we went through in the case study, it gives you a good idea of how using this technique called generative adversarial machine learning is quite powerful to essentially like undo the intelligence that is embedded when you train a machine learning model. What I wanted to sort of consider or put some ideas forward here on what are the platform capabilities when you think of ransomware detector as an overall system, as a defensive mechanism, what platform capabilities can we apply to improve that detection further? So let's consider how, as Lee pointed out, unlike image-based classification where, some pixel perturbation may not be really observable to the human eye, and that's sort of easy to think about. When you generate perturbed logs or modified logs from using this GAN-based approach, for an attacker to successfully use that, they obviously have to go through a number of other steps to make sure that that log can actually be used as as a tool to actually bypass circumvent the model when the ransomware is executing, right? So we sort of looked at like how would an attacker go about using those generated logs, right? So one approach could be that the generated log is used by the attacker to essentially take the original ransomware and combine this log essentially as input into a state machine that essentially finds interesting sequences in the generated log where the ransomware can embed the interesting sequences that they need for the ransomware to actually perform, right? Because a lot of the ransomware is essentially a loop of renaming the files or moving the files, encrypting it, and deleting the original, right? So if you can find within a GAN-generated log those interesting repeating patterns, you can essentially embed spurious operations in them to essentially still run the ransomware, but to the system or to the ML detector, it fits the pattern of this adversarial log, right? Which would mean that you would circumvent the system completely because that activity would look normal, right? So really the only defense against those kinds of approaches is either to essentially make the attacker's job essentially by adding more interesting differentiating features, right, which make it more complex for that attacker to take that log and actually map that into a binary from the original binary to make sure it still actually does the job that the attacker wants to do, right? So that's kind of the bar we need to raise because we are using the information extracted from the system behavior. We can add that other nuances that we're looking for that make the job of the attacker harder. The one other standard approach people use is once you have these adversarial logs, you can just use adversarial retraining to essentially tell your machine learning model that these sequences are still malicious, right? So that's sort of a standard technique that's been used to address adversarial approaches. But because this domain is different from an image classification domain, you can do additional things on the system to make the job of the attacker much more harder. Some other ideas, as we were looking at sort of this track of like what can we do on the system to make the attacker's job harder, is using other sources of telemetry on the platform, right? So for this case study, we extracted telemetry from the OS subsystem for file I/O, right? There is other telemetry that the processor can give you, or other subsystems can give you, for example, through a hypervisor that's completely outside the scope of the attacker's purview, that can give you additional sideband information that can be used by the defense to essentially give you an upper hand, right? And give you sort of an asymmetric information advantage over what the attacker can play with, right, at runtime. And Intel Processor Trace is just one example of such a telemetry where you can extract execution logs of what the CPU is actually executing for a particular application. So as the code is executing, you can basically tell the processor to give you like a running audit log of where execution is transitioning to in a particular kernel or application space. So you can actually profile exactly what system calls were being executed by an application, and this can help you differentiate between a spoofed log versus a log that tells you that truly this was actually executed. Right? The other some sort of technologies or building blocks we've looked at is checkpointing. This is a good tool, and I'll describe that sort of use case in the next slide. The third area is trusted execution, right? So trusted execution gets used as a generic term. What I mean here is a lot of the cases, it's important to actually protect the weights of the model that you're using, right? Let's say you deploy a model on an endpoint, and if an attacker can tweak the weights of that model, they don't really need to go to any lengths to like do any adversarial attacks, right? They can just like change few weights of the model and cause the model to just misclassify, right? But there are capabilities on the platform that can be used to actually protect the model at runtime, so that once your model is deployed, you have a way to ensure that it doesn't get tampered with, right? So we're not as much worried about confidentiality here. We are worried more about the integrity of execution, right? So I'm sort of bucketing a bunch of things under trusted execution, right? And then there are new storage mechanisms like persistent memory that are coming online, starting more from the server side and hopefully becoming available on clients as well. And those give us like completely new avenues to access control storage, right, as the way we think about it. Today, a lot of the ransomware works because you have sort of a common choke point in the kernel where you really don't know who the actor is that's modifying a particular block storage device, right? But with persistent memory and new modes of like direct access to storage through memory, that gives us new opportunities for building access control models where maybe we can wipe out certain classes of ransomware completely. Right? So it behooves us to look at those new models as well. So this is just one slide I sort of I picked on as a way of like talking about checkpointing. Coming back to my earlier hypothetical use case of like you go to a hospital and the system is down because of a ransomware attack, right? So one place we can start with is obviously we can protect the integrity of the ransomware detector or the machine learning capability on the platform itself to make sure it doesn't get tampered with in the first place. The second one is as we are collecting telemetry on the platform, which guides our machine learning system, we can ensure that we use sideband trusted information or in-band trusted information to make sure that that information is not being spoofed by an attacker, because that's an obvious attack point. If I can just modify the data you're classifying on at runtime, then I can just change the decision path. And then using the machine learning techniques of the sorts that that Lee described, you can build early detection systems. Now, no machine learning system is perfect. We are striving to build perfect machine learning systems, but it's sort of it's a journey, right? So, but we can now use these machine learning systems as very good early detectors, as long as we have capabilities on the platform which can be used to drive those decisions and fill that gap of where the portions where the machine learning cannot give you a deterministic a solid outcome, right? Where there's still some uncertainty. And so you can combine, this is sort of an example of how you can combine system-based capabilities with machine learning capabilities to essentially build an overall more robust system, right? So if the system thinks that there is a potential ransomware attack, and you can tune it such that you get very, very low false positives, then you can respond quickly by having local backups and hopefully bring the critical systems back up in an operational state and not affect users, right, more widely. I also wanted to call out just make a plug for one of the tools that we've been working on with in sort of the open source space and with universities called MLsploit. So this is some research we did with Georgia Tech, and it's an open source, sort of openly available tool that can be used by ML researchers squarely focusing on some of these adversarial aspects as applied to malware research, right? So MLsploit is a capability where researchers can come in, they can upload samples or data sets, and you can essentially do like a red team, blue team like interaction on that system, where you can apply research functions to bypass. Other researchers can learn from those bypasses and then compare results and then improve the model, right? And hopefully get common sort of ideas that can be applied more broadly. Right? So with that, we would like to summarize, and I would like to call Lee back up on the stage. With these sort of key points, right, that we wanted to call out. Obviously, ML is a great tool, especially to avoid sort of the brute force feature engineering and get to a good enough solid solution pretty quickly for things like ransomware and other. We just chose ransomware as an important case study. But at the same time, that same ML techniques that we use can very easily be used by attackers as well, and as shown by the case study here. And that has to really, that's super critical in this kinds of use cases, as opposed to like, something like maybe like a photo-based system where it may not be critical if your photo-based system did not identify like a person correctly. As long as you're not using it in a security application, it's fine. But in a security application, we cannot tolerate these kinds of adversarial attacks. And there are other complexities we didn't dive into today that Lee touched upon, like you have to sort of make sure the model stays up to date, is recognizing if there's any poisoning attacks coming in based on the data sets you're using, how is the model drifting over time. And then we feel like there's a very important aspect of combining, especially for these kinds of security problems, combining platform capabilities along with machine learning-based detectors, which can give us a much more overall robust system. So with that, we'd like to conclude, and we'll be in the speaker section if people have more questions. So, thank you.
Thank you.